A very good afternoon to all of you, and I'm very glad to once again invite you all for the PEPS industry lecture. And today we have our IIT Hyderabad alumni, and we are proud of his achievements. We have Dr. B.V. Ravikumar, who is presently scientist F in DRDO. I'll briefly give his introduction, but before that, as you can see on the screen, the title of today's session is Electrical Actuation Systems for Aerospace Applications. So very interesting topic. Before we enter into the topic, let me briefly introduce Dr. Ravi Kumar. And presently, as I mentioned, he's scientist F in head control electronics. And he's currently working in CSL division in the research center Imarat RCI at DRDO. He had a BE from Andhra University in 1998, and he has an MTech in power electronics, electrical machines, and drives from IIT Delhi. So we are very fortunate. After getting MTech from IIT Delhi, he has pursued PhD from IIT Hyderabad on energy efficient drives for electric vehicles, which he has finished recently. Now, his nature of work deals with design and development of brushless DC motors and controllers for electromechanical actuators for following projects. That is program AD and then nearby cruise missile and guided bombs. So design and development of rapid reaction control valves and controller for kill vehicle of PDV for ballistic missile defense program. So design and development of electromagnetic propulsion technology for missile applications. So we have our future Abdul Kalam with us. So meanwhile, he has a lot of awards. That is Agni Award for Excellence in Self-Reliance for development of compact rotary actuation system for PDV warhead gimballing. And we have a DRDO award, he has the DRDO award for performance excellence for development of actuation system for Nirbhay cruise missile. And he also has an Agni award for excellence in self-reliance for development of actuation systems for long-range guided bombs. So with this brief introduction, I would like to pass on the floor to Dr. Ravi Kumar to conduct his presentation. And we have a good number of students joining us, both from power electronics background, power system background, and also I think a few of the students are from different other backgrounds across the IIT Hyderabad. So with this, over to Dr. Ravi Kumar.
Thank you very much, Dr. Pradeep, for introduction. So I would like to first thank Dr. Pradeep for giving me this opportunity to share my experience and whatever work we are doing in the missile area, to especially for MTech power systems and power electronics students. Because always cherish, it will be a pleasure for me to share with youngsters, especially because it is very much required for our country to make our technologies in-house and make in India policy, which our Prime Minister also is more on that. So, and once again, thanks Dr. Pradeep for the introduction. So I'll just go to the presentation, because coming to the topic, in fact, I want to give more on the related to electric drives, but I could not find time, and whatever slides I have prepared for actuation system and sharing with you. Probably during the discussion, we can have more information, and I want the session to be more interactive. And as a power electronics MTechs, probably you have a lot of opportunities, especially in electric vehicles and aerospace applications. In fact, aerospace applications, very few industries are there which are working in India, especially for aerospace. And we are depending a lot on the abroad for importing a lot of technologies. Instead of that, we can have our own technologies and our own people who are graduating from IITs, NITs, and other good universities can work along with this in these applications and can make India this Make India dream true. So that is a concept behind sharing with you all these concepts. So I'll just go through the presentation. So coming to the presentation, I'll just first initially give you about the aerospace vehicle layout, because most of the people probably will be the industries, you will be knowing what is going on, but in aerospace, very few literature is available and very few application oriented technologies will be there in the internet. So I'll be sharing some of the things which are from the drives and power electronics point of view. Even though power systems is one of your core area, I'll be touching because we will be dealing with only power electronics and drives. So that area will be stressed more. And I'll just tell about the control actuation system, what is the design things, all those things. That I'll just briefly go, I'll not go in depth. And I'll just talk about what are the different actuation systems. Like years to year, I think from past 50, 60 years, we were working on the missiles, and we are doing a lot of aerospace vehicles and space vehicles for ISRO also. But there are a lot of evolution in terms of actuation system. So that I'll just touch it, like electrohydraulic, electropneumatic, and electromechanical. So electromechanical is thing which I'm calling as electrical also, because it is more towards electrical. So there comes all the drives and power electronics concepts. So that I'll stress more. And next comes to the future control actuation systems, which I want to, especially you youngsters has to come into that area, because whatever has been done till now, it's almost proven and has almost become absolute in terms of research. But there are a lot of area in which, by combining with other divisions of engineering, because now we can say there is no core research. In fact, we can say it is always a multidisciplinary requirement is there, whether it is a control systems or power electronics or drives. A power electronics alone may not help in a complete enhancement of the system. Similarly, control system will not alone help. So it's a combination of all multidisciplinary knowledge should be there. So that's what I'll be touching some of the topics in the EMA drives perspective, the future requirements, and also some novel concepts and areas. In fact, there are a lot of things which I can talk in terms of applications in aerospace, but I confine myself to few of them. One is because of the time restriction. Probably next time, if opportunity comes, again we can talk more about in-depth design details and in-depth configuration requirements and constraints about electrical machine design and as well as power electronics for aerospace vehicles. So this is how this presentation is made. So coming to we'll start with aerospace vehicle. Basically, whatever aerospace vehicle I am talking can be an aircraft, can be a missile, can be a guided bomb, or it can be a launch vehicle. But specifically, since I am from DRDO, which is a missile complex, so I'll be more stressing towards the missile. But as far as actuation system is concerned, whatever type of vehicle it is, the requirements remain same. Probably some constraints may be different from different type of application. So this is the layout of aerospace vehicle, where you can see there are major things. We can say three things. One is the propulsion, guidance, and control. So these are the main three heart of any missile system or any aerospace vehicle. So propulsion comes to the chemical propulsion, what normally used in all missiles, whether it is a liquid propulsion or solid propulsion. So next is the control. There comes the actuation system. So here in this figure, you can see the fins, which we are calling as a control fin, which is nothing but which will, according to the given command from the onboard computer, it has to generate the deflection in order to give the control force by which the vehicle will be moved as per the desired trajectory. So that is what the function of actuation system, which is a very important, and there lies total power electronics drives plays a very important role. And in fact, we have a lot of opportunities from aircraft industry also, which I'll be coming in terms of technology, what are the opportunities and what are the limitations and where we can improve. So that area also I'll be talking. So that is a control system, and comes in between. We have a guidance. Guidance is nothing but what is the algorithm required to control the vehicle, whether it is a proportional navigation, PN guidance, or whether it is a homing guidance, where we'll have an active sensor, that is seeker, which I am showing in this slide. So that is a sensor. Basically, the guidance algorithm depends upon what type of target it is. Is it a moving target? Is it a standstill target? Or is it a very slow moving target? So such type of things comes under the guidance algorithm. And next comes that is what? Control system, propulsion, guidance. These three are the major important parameters or subsystems in any missile or, of course, aerospace vehicle. Now comes to the control actuation system. So we could have seen in all our control system books in BTech also, we used to see in, I think, in second chapter somewhere we'll be having where a control law will be there through which our actuation system should be controlled. Based on the inertial sensors, the data will be there. And based on that, action system has to move in order to move the total vehicle. So that's how the control system requirement. So the control system requirement is to steer the vehicle on the desired trajectory. So it's a very thing, I'm not going in depth about this. And of course, the guidance function also, we all know it's nothing but it measures the error between a desired and actual position. Based on that, it computes what is the necessary command required to reduce the error, based on which the actuator moves, and finally it corrects the vehicle attitude. So that's what I've written in here, block diagrams. Now coming to the in-depth explanation, Guidance autopilot we'll just forget. We'll come to the controls. The main action of the control is to maneuver the airframe, that is a vehicle. So what are the different control surfaces? We have a TVC actuation systems, and we have reaction control systems, and we have aerodynamic control system. That is what airframe. So the aerodynamic and thrust vector control are the two control systems in which we use actuators to control the vehicle in its desired, to move into its desired position. This is a brief vehicle autopilot system, where this is a control autopilot system of a missile, where we have a rate gyro for taking the rates, and we have missile aerodynamics from which the structural dynamics will be acting, and from which the airframe dynamics will come into the picture. So this is a control block diagram of complete vehicle, and where the actuation system is inner loop to it. That's what I'm showing here, hydraulic or pneumatic or EMA. It's an inner loop to any vehicle missile system. That means it is much faster system. Suppose you want to control vehicle to go to a desired target, your actuation system should be much faster than your outer loop, which is our guidance loop. So now we will come to what are the parameters for the control system design. So that also I'll very briefly I'll go about it. So where we require a lot of aerodynamic forces, what is the inertia, all these things I'm just bringing to you your notice that because the design of an actuation system, which is nothing but from electrical point of view, it's a design of a brushless DC motor or any motor. It's a prime mover basically, and it's power electronics and its control systems. It is equivalent to any industrial application, but there is a difference between an industrial application and an aerospace application. So for that purpose, I just want to bring you as a preface to our actual discussion that what is the criticalities and what are the main parameters for our design. So if you take the major thing is the aerodynamic forces. So this is a very important parameter because the forces are varying. Because if you're moving a missile at a very high velocities, because now everyone is speaking about hypersonic missiles. So tomorrow we cannot rely on a simple missiles or a supersonic or subsonic missiles. We have to go for hypersonics so that our enemy should not be able to detect us. So that's what all we are talking about hypersonic, which is the next generation technology. In that cases, you require a very high aerodynamic forces on the missile. So your actuation system should be able to control that force because you have a huge loads on the fins. So you have to overcome along that load. So your motor design, your power electronics to handle that type of currents and your battery requirements, all these things matters a lot. So that is a major thing. That is aerodynamic forces, which will be varying with respect to the time at a very faster rate. The load is also not constant. And next is inertia torque. Inertia torque is coming from the fin surface. You may have to use a very long control surface to control, which will add the inertia onto your motor because of your control system characteristics will change. And of course, inertia torque due to a control surface acceleration about missile CG because the total missile is also moving. So that inertia will also come as a part onto your actual inertia. So all these things are the major parameters, which first of all, it's not standard. Depends upon the missile aerodynamics, it depends upon the missile velocity, depends upon the missile maneuvering. So all these things are input to your load, from which you derive what is the motor torque requirement. And of course, another important parameter is the surface slew rate. Slew rate is the rate at which you are able to correct the control system. So, and bandwidth requirement. So higher the maneuverability of the missile, your high bandwidth requirement, which again, it's a very important parameter for your motor design, for your power electronics design and control system, where you should use all the current control and flux weakening control techniques. So that's whatever we are studying is a part of MTech curriculum in terms of power electronics and machines. They're definitely and very much useful and very much applicable for all our aerospace applications. And it is very much improves the performance because till now, a lot of hydraulic systems has been using in the aerospace vehicles, which are, I will show the disadvantage, and definitely electrical actuation systems are the requirement of the day. For missiles anyhow, we are already into that. Even for aircrafts also, people are going to the all electric aircraft where you will be using the complete electric motors for propulsion, where you could require multi-phase machines, where you could require inverters with all fault diagnosis. So a lot of huge requirements are there. And huge technical requirement is there. And especially India, if you see, a lot of power inverters, even though we speak about a lot of configurations and a lot of things, we are always buying depending upon the outside world for some of the equipment to be imported. So that all we can overcome by doing our own designs. Whatever we studied, we can just apply as an application and we can overcome all those issues. That's the reason I'm just going in depth about this slide, where I want to show you that these are the actual requirements which has to be taken in the design, and by our application of power electronics and drives, you can overcome all these things. And just this is an overview, because you should know what is for any vehicle. This is not only for a missile, because normally for any aircraft, even it's a fighter aircraft also, you have aerodynamic control, thrust vector control, and reaction control system. So reaction control system is a very interesting control system, which I'll show in the last of my presentation, where I'll show you a video also, where we have done something with respect to very small improvement with power electronics, where we could achieve a lot of improvement at vehicle level. So that I'll come to that. So normally reaction control system will be used at out of atmosphere. Next is a thrust vector control, where is nothing but we'll use the thrust vector will change in order to change the direction of the missile. And is aerodynamic control by the velocity to air, which will act as from the aerodynamic pressure, the force will be exerting on the fins. So by changing the fin direction, we'll steer the direction of the vehicle. So these are the three different type of control systems normally employed in a space vehicle or missile. So next comes to what type of actuation system. So we have hydraulic, electromechanic, and pneumatic. So hydraulic, pneumatic, I'll just very briefly, 1 or 2 slides I'll just show, and we'll directly go to the electromechanical, which is nothing but electrical actuation system, which I'm talking. We'll concentrate on that. This is some just figures.
Dr. Ravi, this is Pradeep. Sorry to interrupt. So I have just a brief observation. So your presentation started on a very interesting note, and it's going fine. Now my question is, some of the things that you are covering today, you might have picked up or learned from your organization, right? So for a student in an institute like IIT Hyderabad or any institute, see some of these things, how they will learn. Is it like after joining an organization they will have to pick up these things, or at the stage of being in academics only, how they can get this kind of exposure to in-depth things? So can you throw some light on that? I don't know whether I'm making sense in asking this question, but I hope you got the thing which I'm asking.
It's very valid question, Dr. Pradeep. Actually, as you said it rightly, for a electronics or electrical, I mean, this type of discussions will not be having at the academic level, but normally this comes from the.
In fact, frankly speaking, we are also, like, as a faculty here, we have our own area of expertise, which may not be, delving into the details that you are covering. So that's the reason why for this series of lectures, we are inviting speakers from industry to cover, to show our students that there's much more beyond, whatever limited things that we handle. So I'm sorry I interrupted. So you can.
No problem. It's a right, valid point what you are telling, but it's exactly right that normally this will come from the industry application only. But if you look into it, whatever I'm presenting, what I'm showing, the ultimate, if you go in depth design, that finally comes to whatever you're teaching only. So what I think, because this is an application orientation. So as an aerospace vehicle, my application may be this, but as an electric vehicle industry, the application may be different. But ultimately, once you go in depth design, it will come to definitely whatever we are learning in the, like for example, mathematical modeling of electrical machines, what maybe probably one of the course you are having. Definitely that is a base for all these things. That's what I will come to that. This is maybe overall thing. This exactly at academic level we may not, and it's not, I don't think it is required also. Means if you're doing for a power electronics subject, definitely we don't expect we to have in details about this application, because applications are also vast. We have different industries having different applications. But what I mean to tell is ultimately all the applications, the root cause will be from the basic. Suppose if you're using a machine for an actuation system, the basic equations comes from whatever you're covering in the academics. So it's only application part, which normally it comes as you join an industry or that thing that we don't anyhow expect in academics. So I don't think that is means it's not very much important also. We should be concentrating.
But then the sessions like this will definitely connect the real world with the academics world. So that's why it is very important. So please continue.
Actually, what I mean to say is whatever we are covering in the academics, they're very much important. Only thing is we have to apply them. So that application will come based on the industry what we are working. So that is the. So this is the 4 actuators driving control surfaces. So just for to have a view like how an aircraft or a missile will have. So these are the 4 actuators which will be used for the roll, pitch, and yaw control, where we use actuators. So this is just eddy action system having a different requirements. As I already told you, what is the deflection and speed, accuracy. So these are the important parameters for design of an actuator. This is a thrust vector control, which already told you that I will show some figures also. I'll come to that. In that I can explain you better. So this is the figures. So if you can see first one, it's a flux nozzle control system. That means the flux nozzle is a nozzle from which the thrust will come out. So you will have a rocket motor front of that, and the propulsion will take care, will happen, and the thrust will come out of this nozzle. And these are the actuators, which I mentioned, pitch actuator and the actuator. They will actuate, they will move forward and reverse in order to control the angle of this nozzle, by which the thrust angle will be controlled and thrust vector will happen and vehicle will move based on the commanded direction. So that commands will be given by an onboard computer based on the desired algorithm. And next one is a jet vane actuation system. This is also a thrust vector control, one of the type of thrust vector control, where you use some vanes. Where the flow is coming out, the vanes will be controlled in order to control the flow. So that is done by actuators. That green one, what I'm showing, is an actuator which will move for, these are called linear actuators. Similarly, the last one, it's a gimbal rocket motor, where complete propulsion motor will be pitch and yaw direction will be controlled. And next comes a control system, reaction controls. Normally, reaction control system, it uses a simple solenoid valve, but I'll just come to that. The last what I already told you, there is a huge requirement for reaction control system, especially in one of our application. So where we use some power electronics controller, very small concept by which a complete scenario has been changed. That I'll come to that. So this is a reaction control system where you have an oxidizer tank and a fuel tank, and both will be coupled to produce the thrust. So valve is an electromagnetic device which will be used for on and off. So this is the actuation load versus actuated load dynamics. So based on the requirements, like why hydraulic action system is famous is, you can see the upper limits of electrohydraulic system is very high. That means it can handle very high loads. Whereas electrical actuation system, it comes in between very less compared to hydraulics. So there the electrical actuation system is one of the limitations of the electrical actuation system is its load capability. Now the problem lies with the electrical engineers to make electromechanical actuation system more power. More capability. That is where the challenge lies. That's what I'll be coming to that also. And this is, of course, whatever I covered in the last slides, same thing is summarizing here. So this is the control system. It's a very simple thing. We have a servo electronics. We have a power inverter for driving a brushless DC motor or a stepper motor or SRM, whatever the motor it is. We should require a power amplifier, servo electronics, and it acts as an actuator. This same thing. Now I will not go in depth about this because this is not our topic actually. Just I want to tell you what is the merits and demerits, because based on that we have to develop our electrical actuation systems. So the basic elements of hydraulics is we require a hydraulic power source, and we have a servo valve. And the main merits of that is it's having a very high power to weight ratio. And limitations are a lot of subsystems are there, and it is continuous leakage of oil. So it's require a lot of maintenance. But all aircrafts, what we are flying, commercial aircrafts, use hydraulic actuators, and all space vehicles, launch vehicles like PSLV, GSLV, first stages they use hydraulic action system because of load carrying capability. But they are having a lot of limitations. There is a contamination, leakage of a lot of maintenance is required. So this I'll just skip this slide. This also I can skip it because it's about hydraulics. And there's only some figures I want to show you. Prithvi, which is our first generation missile, surface to surface missile, which is using a hydraulic action system. Agni and the PSLV, these are all using hydraulic action systems, where the heart of the hydraulic action system is a servo valve, which we are calling as a electro-hydraulic servo valve, which is the heart of an hydraulic action system. So this is a brief construction in which it's also not very much relevant to our thing. So I can just only explain you about this. I can skip it. So these are different electro-hydraulic systems for different missiles. So these are just figures to tell you actual hardware figures so that you'll get a feel of how a nozzle looks. So this is the nozzle, and in front of that is you have a rocket motor, which is for different actuation systems. And this is a hydraulic actuation system where you have an actuator for actuating the engines. So this is the first generation missiles what we have. Now we'll just go to electro-pneumatics, which in fact we can tell absolute. We are not using in any of the missile these pneumatic action systems, because it also has same problems with hydraulics, but in fact it is much lesser torque to weight. I mean, compared to power wise, it is much lesser than the hydraulic. So it became almost absolute. Only in Akash missile, we have these pneumatic actuation systems. So this is also similar configuration of hydraulics. Only use pneumatics instead of hydraulics. So these are some of the Akash missile where we're using these action systems, the pneumatics. So this next we will come to the electromechanical. So there actually we will concentrate more. So basically any device you can use which will convert electrical signal to create a mechanical movement for this actuation system. That we will call it as a prime mover. So we can use a brushless DC motor, we can use a brushed DC motor, we can use an induction motor, any motor. So in this also we have, one is a linear electromechanical actuator, rotary electromechanical actuator, and most of the action systems in the missile throughout the world, not only India, not only missile, even space vehicles, wherever we're using electromechanical, we go for either brushed DC motor or brushless DC motor. And now brushed DC motor also nobody is using. Everything is shifted to BLDC motors. Only in first generation small missiles we are using brushed DC motors like NAG and other things. But otherwise all missiles now we are using BLDC motors for our electromechanical actuation systems. So now we'll see brief components about actuation system, electrical actuation system. The major, whatever I tell, heart of an actuation system for hydraulics is servo valve, whereas heart of electrical action system is the servo motor. That is it can be a BLDC or any motor, but it's a servo motor. So, and we have its screw mechanism. If it is a linear actuator, it requires a screw mechanism. Either it can be a ball screw or roller screw. And it requires a feedback sensor, which can be an encoder or it can be LVDT. So these are the major elements. And out of them, the major, and you can say the heart of the total system where complete bandwidth, complete dynamics, complete load requirements will come from the servo motor. And this is, of course, the sizing where we require material selection, what is the configuration, and main is the power plant sizing. There, actually, that is the area where electromechanical actuation system is lagging behind hydraulics. Because the moment you require high power, your battery requirement will be more. So your power plant sizing is very important. And there your design of the machine, design of power electronics, and total action system design lies. And I'll just show some of the configurations. Inline configuration means the motor will be directly coupled to the screw mechanism, where the motor direction can be controlled by which the screw will be moved forward and reverse. And next is a parallel configuration where you have a gear drive to reduce the speed and increase the torque so that the motor torque can be enhanced by the mechanical combination. So that is a parallel configuration. And we have a rotary MA in which there will be no screw mechanism, only motor coupled with gears. So these are different configurations with electromechanical actuation systems. Now these are the different actuation systems which are developed for some of the missiles. Like we have Astra missile, which is an air-to-air missile. We have a different actuation system having different power requirements. The reason behind showing this slide is we have a different actuation system requirements for different missiles. It's not one actuation system cannot go in all missiles. Based on the space requirement, bandwidth requirement, and force requirement, the actuation system design will vary. So now coming to the basic designs and what are the design criteria we have to do. So that is the electric motor, as I already told you, it is the main thing. Next, we have gearbox, roller screw mechanism, which mechanical elements, and the power supply unit, and major one is the controller, where complete control algorithm, whether it's a current control or voltage control, the control system compensators, everything has to be taken care in the controller. So these are the major systems for and basic elements for servo motors. Then we'll see what are the merits. It is a modular system, no leakages, nothing. It's like an electric vehicle. You can compare this with an electric vehicle where you're driving with only motor. So definitely compared to hydraulics, it's always better because you don't have much subsystems. It's very modular system, no leakage, very low maintenance. Coming to the limitations. So this is the area where we have to work more because the industry is moving towards all electric aircraft and even electric propulsion is one of the area in missiles also we are working on. So what are the limitations? Low operating time, high inertia, and moderate stiffness and high surge current requirement. These are the main things. That is the low operating times comes from the battery or low operating time because of the temperature of the motor and also the power electronics. So these are the areas which we have to work on to make it more usable for all applications, including aircrafts. So this is the basic block diagram, how the control is done. We have a motor controller, motor driver, transmission mechanism, and from which we are getting a position as a feedback, and velocity current can also be used as a feedback based on the application. This is a complete block diagram of actuation system. Now in depth, if you go a little bit in depth, we have a power inverter. Basically, all my slides will be talking about the BLDC motor. So the power inverter, what I'm talking will be for a BLDC motor only. So definitely, I will come to the what are the next level challenges and next level developments, which main I'll stress on that. But whatever slides I'm showing now will generally speak about BLDC. So this power inverter is a hex bridge inverter where you will have six MOSFETs to control the BLDC motor. It can be a trapezoidal commutation or a sinusoidal commutation based on the application. So this is the hex bridge, and we have a EMI-MC requirements. That is one of the major requirements for any aerospace application, because all the power source will not be common to the actuator alone. The power source will be shared among different subsystems. So that EMI-MC design, which is a critical design, is a very much important for any actuation controller. So that's what I'm showing in a block here, which is nothing but a EMI-MC filter, through which it will go and finally go to inverter. From there, we have a BLDC motor, and we have Hall sensors for the sensing if it is a trapezoidal control. We have encoder for some of applications where we're using a sinusoidal control. And we have a separate controller based on our communication interface with the OBC. Onboard computer, we have different communication protocols as per military standard. That communication protocol has to be included. And finally, complete control will be done by the controller, which will take the current sensor output, which will take the position feedback output, velocity feedback output, and complete control algorithm resides in the controller. So in the nutshell, this is the configuration where we have power amplifier, a controller section, and a signal conditioning system. We have processor stage, signal conditioning stage, and power stage. The combined it will become a controller, and finally it will be connected to the motor to control it in a closed loop. Now, what is the advantages? I think we don't need to go much on this. We already know these are the major advantages of electromechanical because of no maintainability. So high reliability for all aerospace vehicles and all missiles now, it is completely going into the electromechanical actuators only. Even the space vehicles, what ISRO is doing also, they want to go for electromechanical of very high power. So, but there are some limitations which I will be covering next slides. So coming to the configuration design, servo design, motor design and selection, power electronics and control design. So these are the major things. So coming to the EMA, this is already explained. We have different EMS linear rotary, and we have also controllers which are digital analog, and analog nobody is using. It's completely digital platform now. So coming to the servo design, this will be something interesting to you because this is the area which has to be more concentrated for all actuation systems, because there are a lot of constraints and requirements coming from the missiles day by day. So position loop, normally LVDT, incremental encoder as a sensor, which we use a optical encoder or magnetic. Normally we use magnetic encoder because of its reliability and ruggedness. Magnetic encoder and potentiometer, normally we are avoiding because of its own problem. Normally it will be an incremental encoder or LVDT as a position loop. And velocity loop, either it can be derived from encoder or we can have a tacho if you want to have a higher velocity gains. And for current loop, for estimation of disturbance torque, which we will call it as a feed forward loop and current commutation. So we have a very interesting requirement for especially for aerospace vehicles. There will be a lot of uncertainties when the vehicle is flying, because a lot of things you cannot estimate unless you test, and you cannot wait for your testing because you test finally in the air only. So you have, of course, you have some setups where you can simulate the air conditions on the ground, but still there will be a lot of uncertainties once the flight is flying. So our system should not be, we should not learn anything from the flight. We should design everything and we should fly it. We should not afford any failure. So for that, the major things come from the controller design, because we have a lot of uncertainties. One is the aerodynamic load. One is the major thing is the opposing and aiding loads on the actuation system. So your control loop should be designed such a way that you should not have any difference in the aiding and opposing loads, for which you require a very tight and high bandwidth current loop. So it should require in the terms of 10 kilohertz current loop you should have to control your actuation system perfectly in aiding load as well as in opposing loads, which is 100% aiding and 100% opposing loads. So that means what will happen if you don't able to control it? What will happen is if suppose in aiding load, if you're not able to control it, you will have a huge overshoots, which will eat away your margins, control system margins, because of which your vehicle may become unstable. So these are the areas which is very much required for any servo design. So you should have a very good current loop, velocity loop for having high damping, and of course position loop, because total system itself is a position control system. they require a position loop as an outer loop. So this is how the servo design starts. So here the main element is the plant, because you have to design a motor first of all to able to control in this way. Because if you're designing a motor with a very high inductance, probably your aiding load you will not be able to control. Because of high inductance, you cannot control in the aiding load, and of course you will have a lot of speed drop in the machine. So these are the design parameters we have to take in the right from the beginning of the design. So I'm coming to the motor design. Just one slide I'll show you about the motor design and criticalities of any drive design. Not only motor, it's a motor plus power electronics. Because the major thing is in any machine, whatever you can ask me one question, why there are a lot of companies. Of course, in India, unfortunately, we don't have any company who design a servo motors. We have a lot of students presenting a lot of machine designs, but unfortunately, everything we have to buy from outside only. Like you name any company like Fallhober or Kilo, some of the companies which we call it as Cermat, all those things are very famous motor designers, and we are buying them for some of our applications. But definitely, off-the-shelf motors will not give our requirements, because a motor designer and control designer and power electronic designer should be same as far as I am concerned. Because motor alone, if you design, you don't know what is the current control it is doing. You don't know what are the harmonics are injected in the motor. You don't know what is the PWM frequency it is operating. The motor design is incomplete. If you're designing a power electronics drive without knowing what is the motor actually doing, what are the type of transient it is happening, what is the type of aiding load it is coming, then it is not a perfect power electronics design. And as a control system designer, combination of power electronics and motor should be combined to meet our actual requirements. So it should be whatever, like power electronics expert we are telling, it should have complete knowledge of machine design as well as power electronics and control system. Then only better product will come. Otherwise, we can simply buy a motor from the outside. Then we have to design our power electronics according to that motor, which in some applications may work, in some applications it will not work. So what I meant to say in this slide is, this is the motor design which normally followed. At our place, we design all the motors in-house for our all missile applications as well as space applications. Like we start from the torque, speed and voltage, and we'll arrive at the motor design parameters. The magnetic design, where there are a lot of materials, selection of magnetic materials, right from it BH characteristics, its magnetic properties. It's very much to start from the beginning, because any outside motor you're buying, normally they rely on the commercial applications. They will use a normal commercial material, because the cost is important for outside industry. But for aerospace, also cost is important, but some of applications, the performance is more important than cost. So that also we are coming, like we should have more performance as well as low cost. That is one more subject also I'll just cover. So selection of magnetic materials, derivation of the magnetic equivalent circuit, and all these things are the standard design procedure for any motor. And next comes the electrical design, and finally you, based on your optimized parameter, to design. So this design should include your control system requirements. So you cannot design motor separately. It has to come from the control system requirements of our application. Next comes the control design. Now comes to the control methodology. Probably this very much you will be learning in your power electronics MTech. You will have a lot of flux weakening control, all those things, but they are very much required for the industry. I'll tell you. Now, since electric vehicles are into the market, we have a lot of ICs which are having all controls in the single IC solution. Like Texas Instruments, they are having ICs where they have their own algorithms, which we call, I think, iMotion or something, which we are giving everything. But actually, industry, if you take, it's like it's not very much required for some of the applications. Like BLDC motor, frankly speaking, FOC is not required, because as such BLDC itself is designed with a QD axis with 90 degrees to each other. So, but the industry is projecting some of the ICs in such a way that it can be used everywhere, but it's not so. It depends upon the application. If you're doing for a voltage control, it's simple and easy to implement. So some of the applications where we don't require aiding load and opposing load, then you can just simply we have to go for a voltage control, because it's very simple and there is no uncertainties, and that doesn't depend upon the current sensors, noise and all those things will not be there. It will be simple. Coming to the current control, the faster response, you require accurate current sensing. So whatever industry ICs, all those things projecting, they have their inbuilt current sensors, but definitely they will not work. I mean, they will not work to that level of sensing. So that depends. So we have to make our own custom requirement based on our requirement, based on our type of currents handling. We should be able to design our own control. And coming to flux control, this is a flux weakening. This is very much important in terms of the machine as well as the control, because from the motor point of view, all battery voltages we can reduce if we can improve flux figuring control. That's what we are doing for the space vehicles. We're employing the flux figuring control so that the battery voltage we can no need to go for high voltages. Normally, the velocity requirement in a missile or an aerospace will come whenever there is a demand from the system. So the demand will not be continuous. So for that, we no need to carry a high voltage battery. So that's where we can overcome the hydraulic actuation systems, where even for high power wattage also we can use BLDC motors and actuation system, electrical actuation system by employing flux figuring control, which already is being done. So the main criticality flux figuring control is well established in terms of controller. There is nothing new in that, but only from the motor point of view, the main difference for the motor, the capability of the motor should be for flux figuring. That means we should be able to give the torque as well as the speed extension. That from the motor design, the main criticality lies. So coming to the power electronics, it's a very much important area. Normally, in fact, we have a lot of power electronics experts in academia and industry in India, but unfortunately, we are buying a lot of power electronics drives from outside. So there is a famous company called Elmo, which I am talking to every industry in India to make it, because this is a Elmo motion control drive, which is from Israel, which is, we can say it's a best. It's an excellent motion control system, which everything is lies in a one ASIC. So they developed their own ASIC with all sorts of control. It's a very good device, giving an excellent performance. It's being used in a lot of new generation missiles. But I want to make this in India happen because we have a lot of experts from academic. We have a lot of students, youngsters like you, who can use this very simple techniques are available, which we are already studying. Same thing we have to apply to our application and make our own controllers, which will come from India. So in this main thing is what we can go further is we can go for SiC MOSFETs, which already industry is doing. There is no doubt SiC people are using for all high power applications. And we can go for a GaN devices if you are going for very high frequencies. Probably that may not be required for power electronics for drives. So that will be the one of the area. And efficient thermal design, especially for actuation systems, that is very much important because we have a huge currents. Because actuator has to move in a very high frequency, 30 Hz, 40 Hz bandwidth we have to move. So always the actuation system will be of that range, the current requirements in that small space, because we want to reduce the weight. So obviously thermal design should be very efficient. And of course, high combination frequencies, because all the next generation missiles, we have very high speed actuation systems. Now itself, we are going up to 30,000 RPM. So once we are going for a very high speeds, the combination frequency should be very high and our losses should be minimized. So this is one of the area from power electronics and devices point of view very much is required. So this, of course, kinematic design of an actuator. This slide I want to show you because the torque depends upon the motor. It depends upon the inertia. It's a very famous equation, but here only the uncertainty comes from the inertia because there will be a inertial variation once the vehicle is moving. And also the load torque I not mentioned here, that load torque is uncertain. It can have an aiding or an opposing. So this, based on this equation, the total sizing of the motor will be done. This is of course same thing. So now we'll come to the, I'll just skip this. It's again a component design where most of the mechanical things are there. And coming to the BLDC motor, it's only the stator and rotor, which already covered. This is about the transmission mechanism. This is again the gauge trends, which we can just go through it. Yes, this is one important slide I want to show all of you, which very simple basic equation what we have studied in BTech, but this equation never actually follows the actual result. So it's a very important thing which normally any industry motor drive designer will not give any information of its speed torque characteristics. He will just give speed torque characteristics based on this equation, which is not at all true when you actually design a motor. So there are a lot of parameters. The major parameters, the inductance. In fact, I want to show you a model and application where the inductance affects. So that I could not show you because of some time problem. I could not prepare that. But why I'm showing this, whatever this it's saying, absolutely in the practical, you will never meet this because of various reasons. Like one is the magnetic design of the machine, whether it's done by any company, name it any big company also, it will never meet this because you have a magnetic design, which is a very important parameter, which depends upon the saturation of the material. So that will droop your speed much beyond this equation. And very high speeds, you have an inductance parameters, which normally will not be given in any of the motor data sheet. And this all will affect your control system design. So the major thing of showing this slide is this, as a motor, I can give this, but ultimately this will affect your control system design in which you will have a lot of overshoots because your speed is not the desired speed. as the load is increasing, you are operating at a very lower speed. So you're not able to meet the required specification. So you'll simply keep the increasing gain, because of which you'll ultimately result in increasing the overshoot. So these are the very much important parameters which, as a designer, as a machine design, or as a from the power electronics, then you can go for a flux weakening in that cases to increase your base speed. Of course, then your actual torque requirement may come down. It depends again on the motor design. So these are the important parameters we have to look into it during the design or during a selection. If you go for a control system designer for any company, also should be able to understand the servo motor, if not design the parameters of the servo motor, should be able to model it. Then you have to use for the application. Next, coming briefly about the motor, I'll just show major parameters. These are the major configuration, speed, all those things. And this, of course, it's a general thing we have to during the assembly check. Then these are some of the specifications. Just I want to show you what type of forces normally we work. 25,000 newtons, that means 2,500 kg force. These are the actuation systems we are using. And this will go to something like 25,000 kg force if you're going for a space vehicles. So your actuator has to give this much high forces. So your design should be so robust enough to take this type of loads. So these are different components just to get a feel. This is the stator and rotor, which are all being used in missiles. These are the kit-off parts type of thing, which are developed as separately within our local industries, and we are using in the missiles. This is about the control system design. Major thing comes from the BLDC motor and its parameters. This here also actually we have a three-phase machine model, including all sorts of inductance effects and all sorts of device effects. We have a model, but that I could not bring to you. It's a single phase model. Here actually BLDC motor is modeled equivalent to a DC motor. This is absolutely not correct. We should have a three-phase model, because the three-phase model will only give you exact picture when you're operating at higher speeds, because the machine is switching from one phase to other phase while it is running. So each time the inductance of each phase will have its own effect in the total current rising. So that we have to bring out in the three-phase modeling. But this is, I think, old slide, it was same like that. But this type of simulation first we have to do, from where we have to arrive at the actual parameters, and we have to go for the design. These are the simple step response, the actual hardware and final model. So this is different. This is what I am telling. Currents. The current requirements will be very high during step response. And we have to handle this type of currents frequently if you're going for a very continuous type of step commands. And this type of step commands are very much required, which is very much expected in the actual flight conditions. Now we'll come to the critical element. What are the present technologies and what we have to do? So coming to the brushless DC motor, I think now brushless DC motor as a research, I think we can make it as an absolute, because BLDC motors are completely coming to the EVs, electric vehicles, and people are, even industries also well matured on this. So there will be, we can say almost BLDC motors, we can say at the verge of absolute in the research point of view. Commercially, people are coming now and they are using for EVs. Definitely there is a lot of requirement, but I'm telling from research point of view. Stepper motors, of course, these are also very used wherever the open loop requirements are there. Next comes the switched reluctance motors. In fact, this is not a present technology. I might have made a mistake here. SRMs is one of the area which is very much required for servo application. Normally, nobody tried it for a servo application. Normally, for EVs, they are doing it. That also I'll come to the next slides. Then we will ask why BLDC motors are so famous. Because what is the requirement for a servo drive is it should have a linear speed torque characteristics, it should have a linear current torque characteristics, and simple and robust control. All these things are possible with BLDC. That's why people are not just moving away from BLDC. Because as far as I know, I joined in 2001 in RCI, and right from day one, 2001, actually first time we imported a motor from outside, and that we started our own design in 2002. From there onwards, we are using same BLDC motors with a little bit improvements in terms of design, but not in terms of technology. But definitely now industry is well matured. When we started, industry is nowhere in BLDC motors. Now all industry, in fact in Hyderabad itself, we have some few industries which are doing BLDC motors based on our experience they are doing, and even they are doing for EVs also. But why people are not moving BLDC is because of these advantages. But at the same time, of course, I'm not showing any disadvantages. Of course, I'll come to that. So I'll just take another 10 minutes. Is it okay, Dr. Pradeep? Am I running out of time? Any other? Dr. Pradeep?
Yeah, it's okay.
Just
I
5 minutes,
will.
I'll complete
Yeah.
it. So then, which type of actuation system should I use? This now by this time you should be able to understand that for a high power you have to go for hydraulics. For stiffness, high stiffness you have to go for hydraulics. So these are the disadvantages of electromechanical, which definitely from power electronics, whatever control techniques I told, we can overcome that. And response, of course, electromechanical we're going up to 35 Hz, and size is also, it is compact compared to electrohydraulics. So normally, in fact, put these comparison chart aside, we can say for all missiles now we are using electromechanical. Not only India, all over the world. Coming to the launch vehicles, people are using hydraulics, but that also they're shifting to the electromechanical. So we can say aircrafts, people are going for actuation system, electrical action, that's electromechanical. And propulsion, which we are telling are all aircraft, at least for passenger aircrafts with the short distances, even for propulsion, it's going for electrical systems. So it's a complete electrification, as we tell in the electrification of transportation. Same thing is happening in the air also. So aircrafts also becoming all electric aircrafts. We have a loitering missiles, which is completely electrical. There is no chemical propulsion. That is also one of the area which is very much required. It's a complete electric propulsion is going on. So power electronics, electrical machine design plays a vital role in all these things. So electromechanical, the major disadvantage from this slide, you can say the power, but that we can overcome with a combination of new designs, which I'll just show. I'll be showing only one or two topics, but there are a lot of topics which definitely can be worked on. This is one more technology, which of course I kept here, but it's a hydrostatic actuation system in which you use an electric motor for the control of pump. But obviously, this is also not people are using; they're going for complete electric. So this is one of the area which in fact I'll not touch, it's a smart materials. Now we'll come advances and future. So this year we'll spend little bit time. Now more towards electrical actuators even for high power, high bandwidth, dual redundant applications. So this is the requirement because now we want to use the action systems everywhere, electrical actuators, even for space launch vehicles where we're telling high power also we'll go for action systems, electrical only because of its advantages. Next important thing is the magnetic gears and direct drive actuators. So here you will get a lot of topologies in machines, especially transverse flux machines and 3D flux machines, where you can go directly for direct drive applications. And magnetic gears, which is a very hot topic and a very interesting topic in terms of magnetic gears, where you can completely eliminate mechanical gears, and you can have more advantages in terms of efficiency, and backlash can be removed. And advanced control and power electronics for high power action systems, where you can combine the power electronic power inverter with a boost converter to improve the voltage requirements as normally done in the electric vehicle. Same thing can be applied for aerospace vehicles also. And new fault tolerant high power density drive configurations, which is very much required for aircraft propulsion, where the redundancy is a must. So these are the areas which has to be worked and where the power electronics control and electrical machines plays important role. Now coming to the drive configurations, axial flux BLDC, which normally China is doing a lot of activity on this, and unfortunately India, a lot of motors, I can say, a lot of motors are being for electric vehicles. In fact, a missile complex, all these things we are doing, but for electric vehicles, people are totally residing in outside world, and especially for drones and this type of applications, because ultimately the next generation will be the drones, where everything is coming from outside the world, because we are making one of such application where the industry is completely depending on outside. We are having so much technology with us, so much of human resources, and we have a lot of academicians and a lot of students are coming out from IITs and IIS and NITs. Still, we are depending for the machine design and fabrication and this type of technologies outside the world. That is one of the part which, as an industry, as an academicians, we should work out and bring our own technologies in the market. So axial flux BLDC only limitation is it's a material which normally soft magnetic composite should be used. But there are research organizations like ARCA where they're using the SMCs for developing this type of machines, and this will be used for more for electric vehicles. For aerospace applications, this may not be that relevant, but it's very much used for electric vehicles, and which is a very much important for nowadays industry because all industry is moving towards EVs. And Hallback magnet motors and interior PM motors for efficient flux weakening. So these are the major areas. And of course, this I will not touch much upon this because the time is, I think, running out. I'll just go through this. One of the area where we have used a dual rotor Hallback BLDC motor, which will be used for increasing the efficiency of the machine. So now this I'll just spend small time. What I want to say is the controller combined with a boost converter, because such type of things we have to do it to make actuation system useful for high power applications, because especially for aerospace, it cannot be used for a normal industry or electric vehicles. But aerospace, what is happening is the requirement of the velocity will not be much. The velocity requirement will be where whenever there is a demand from the OBC or onboard computer based on the vehicle dynamics. Some missiles may not be continuously requiring that velocity. For that, we no need to carry a very high voltage battery. We can have an interlever boost converter with a very high frequency GAN devices, or you can use even SICs also. And we can use a boost converter to boost the voltage based on the voltage requirement, based on the speed requirement. That is what this type of combinations can make total system useful for even for electric propulsion applications. So that is the point in showing this slide. And fault tolerant applications. These are the one of the fault tolerant application which we have done for different various missile application, where we can use two stators in a single housing, so that the stators can be switched based on the fault. So these I'll just go through it. There are some simulation results also. I'll just go. Now I'll come to the direct drive actuators, which is one major area, especially for here. If you see the literature, there is a called a transverse flux machines, which is very much required for a direct drive actuation systems in missiles or in aircraft applications, because you don't require, frankly, any transmission mechanism. You can go directly as an electrical thing. We don't require any mechanical elements, so no gears, no jamming, no backlash. So all those things can be overcome if you're using direct drive configuration. Further, you have a high force density tubular linear motors, and the reduction of cogging torque and such type of techniques can be employed. And major thing is the transverse flux machines, where we have to use a 3D, which we also call as a 3D flux machines, or we can use SMCs, soft magnetic composites. This is one of the actuator which is developed with the Hallback concept. This is a very famous concept which nowadays all the Western world already shifted to this type of designs for aircrafts. So this is where we can improve the power density of the machine. This is just a design flow chart which is equal to any machine design. So these are the different hardware where we can have Hallbacks to improve the power density. Now this is the slide which I just wanted to show you, which we are calling, which we use it for important projects, which we have improved the performance of the valve by using a simple technique of switched MMF. Because if you take a solenoid valve, it looks like a normal mechanical element. But if you go in depth, it's a more electrical engineering is involved in it. The major thing is, by using this concept, we could able to completely reduce the weight of the missile, and as well as the response times are reduced from 100 milliseconds to 6 milliseconds. So this here, one small video I'll just show you so that you can appreciate the way of happening in the actual missile. Okay, so this is what why I've shown is, this is what we are calling as on-off control system, where we use valves, electromagnetic valves. That is nothing but a solenoid valve. Here, what we have done is a QRSV on time. Earlier, it is around 166 milliseconds, which has reduced to 6 milliseconds, because of which we could achieve the complete kill probability of the vehicle. The complete maneuverability of the vehicle increased because of the reduction of the time. That means the response time has been improved by design of the magnetic material, by design of SSMF, by which the current is controlled in the valve. Instead of pumping a constant MMF throughout, we changed the MMF because the reluctance is varying in terms of a solenoid. It's not like an electrical machine where the reluctance is constant. Here the reluctance is varying based on the plunger position, because of which the MMF can be switched based on the requirement. By doing so, the complete on time has reduced from something like 66 milliseconds to 6 milliseconds, because of which the complete controllability has been achieved, and it has been excellent performance in terms of actual flight. So this is how, this is just a slide, a small application. This is what I want to show you is the combination of power electronics, electrical machines, and control system can do a lot of things in aerospace industry. Nowadays, all aerospace industry is moving from actual conventional hydraulics to electrical, and there are a lot of requirements. In fact, there are a lot of things where from the DC-DC converters, all those things are there, which I am not presenting here, but that background that that's I want to tell you. Of course, this is a magnetic gas, which I already told you. So that's all. So I just want to conclude because I think I already some 2-3 minutes over. This I just covered about different type of action systems and what is the design methodology. Probably I'm not gone in depth about the design. Just I'm showing you that what is the important areas like electrical machine design, power electronics. Also, I have not gone much into the device selection and the gate drive circuit design. All those things are not gone, but that is very much required. Which I can definitely next time if we have opportunity we can talk about that. And what are the new things we want to work? We want to work about the combination of different things like a power electronics inverter as well as boost converter and actuation system with a different type of machines and going for multi-phase machines kind type of things can be done in order to make action system more robust and more useful in the high power applications, especially in terms of aircrafts, electric aircrafts to make it all electric propulsion also we can use this type of concepts. So that is overall thing. So thank you. So thank you very much. And if any questions are there, you can please ask.
Excuse me, sir.
Yeah.
Can you tell me about the applications of sensors and communication systems in defense?
Yeah. Sensors actually, if you take as a vehicle alone, you have a huge sensor requirement. And in fact, we are depending on a lot of sensors in outside world also. The major thing, if you take sensor for guidance, like we have a IR sensor, infrared sensor, which will be used for the homing guidance application. We should have the infrared image of the target. So that IR sensor, which is a very much signal processing and image processing oriented, that is one sensor which we require at the vehicle level. I'm telling about the missile level. Next is the navigation sensor, which RCA itself is a pioneer in navigation sensor department, and we have done a lot of INS applications for different missiles. So navigation sensor, these are the main sensors at the vehicle level. And coming to the communication, normally as a weapon system, we have a lot of communication requirements because if you are flying a missile as a weapon system, I'm not telling about the onboard communication. I'm telling at the communication with respect to the radars and communication, wireless communication. It is very much proved and we have a lot of requirements because the data rates what we are talking will be of very high in order to get the better data from the radar for our onboard computation. And coming to the inside actuation system or inside the onboard, like communication between the onboard computer, INS, and our actuation system, we use normally different type of communication. One is the mil standard 1553 is one of the communication where we use because it's a robust enough and it's a dual redundant communication that is using. Normally, we use this type of communication all of the missiles. Coming to the communication and coming to the sensors at the actuation level, we use encoders for position sensing, and we use same encoders for velocity, and we use a linear variable differential transformers, that is LVDTs for position sensing, especially for linear actuators. And also we have magnetostrictive sensing, and we have magnetic encoders. Also we are using for some of the applications. Yeah, I think that's the what. Is it okay?
Okay, sir. So,
Sir,
what are the knowledge? So, what is the knowledge and skills do I require to work in the area of sensors and communication systems?
Coming to the knowledge, basically, frankly speaking, anything knowledge we require, only major thing what we require is a mathematical modeling of anything. We don't really require, even if it is a power electronics, even sensor, the major things, the physics we should be understood. So the mathematical modeling. So right from your college days, we always want students or the youngsters who are joining RC or DRDO also. We want the mathematical skills. That is very important because unless we model a system, because normally if a sensor, suppose INS is there, what we are getting from the INS is the acceleration rate data. So the data we extend, we have some code which already developed by predecessors. We have to, it is not that we have to maintain that code. Only thing is we have to model the system and fault diagnosis. So such type of techniques is very much required. So coming to the knowledge, probably whether it is any background is electrical or electronics background, it is sufficient to work on that. But only when we come here, we should have that strong mathematical modeling skills to improvise on the existing system.
sir,
Yeah.
yeah, good afternoon, sir. Sir, I have one question
Yeah.
regarding, sir, I wanted to know, like, sir, uh, in order to join DRDO institutes, now DRDO is not recruiting MTech and PhD students. Then, sir, my point only was like, are they are able, means that like you are working there for 19 years or 20 years, sir. Now you are, means like the BTech candidates which are coming, joining DRDO, are
Yeah.
able to, means they are okay, sir, means you are able to manage.
Okay.
My
This is
point is
that,
suppose,
anyhow, that is a good question, but I don't know. I cannot answer that directly because I am handling very few of them who are very good. Definitely, BTechs who are coming. First of all, we have our own type of what you call recruitment policy. Probably we'll get a very good students. There is no doubt about it. It's only how we use them. Definitely, everybody is expertise in one area. There is no doubt about it. It only depends on how we use them. So, and of course, that probably it's more related to HR question. So, but as far as I am understood, whoever are coming, it's not because everything is basics only. I don't think we are doing which is against basics. It's everything from basics only application. So whether it's a DRDO or ISRO or any other organization, that questions remain same thing. So probably depends upon the application how the what seniors use them. That depends on that. So that's all I can
because
answer.
sir,
Dr.
because
Ravikumar,
opportunity.
Dr. Ravikumar, can I rephrase that question? So
Yeah.
let's say, I mean, maybe the student may appreciate this question. Let's
Yeah.
say somebody has completed MTech. Okay.
Yeah.
Now they want to, contribute for DRDO.
Yes.
So how do they do it? Because if you recruit at BTech, how
Yeah.
can MTech or how can a PhD person
Yeah.
contribute to DRDO?
Compared to a BTech,
Yes.
or yeah.
Yes, not in comparison. In what are the ways in which an MTech graduate can
Yeah.
contribute to DRDO?
Yes. Definitely, because if you take a suppose I'll just an example. Suppose MTech Polytonics guys starts joining in DRDO. We have a huge requirement. I mean, huge application orientation is because a lot of research is pending. In fact, I can say a lot of research areas are there which we are not having time to do. In fact, that word I should not use because time is already always be there. But it's frankly speaking because there are a lot of research areas which we are not touched. In fact, India itself is not touched. Suppose if you take electromagnetic propulsion, which are not covered here, it's a huge area where you require a lot of high voltage requirements and a lot of power electronics requirement, a lot of modeling. And from machine also, you should design a very high speed linear induction machines or linear BLDC motors where nobody in industry has done. Because for that application, I've gone throughout the India. I have already a lot of people have spoken, but very few people are in that area and they are also not up to the mark. Industry wise, I'm telling. So from research point, that only we have to do. So only research as a research organization, DRDO is ready to do a lot of things. At the same time, we require the expertise from out, like youngsters has to join. So that expertise definitely can, suppose a Polytonics guy use, there are a lot of areas where we can utilize it. We cannot say one area because DRDO as such is handling a lot of technological areas, which I have spoken only, I think, in a droplet in a ocean, what I told you. So definitely it can be used in a different ways. There are huge applications, right? From radars to missiles to even tankers to everywhere. Wireless power transmission is one of the area. Wireless power technology, where we want to make complete missile without wires. Because we want to, as I shown you that valves, which I'm showing you, there are a lot of 40 valves out there in a small space. So if you remove completely wires, you go for a wireless power transfer. You can go for a surface power transfer, which already University of Buffalo is doing for us. So this type of things, a lot of applications are there which can be utilized from whoever it is joining, whether it's a Polytonics or control systems or any candidate. So hope I think I answered that.
And sir, one
Yeah,
more
any other
concern.
questions?
Sir, one more point just I want to add, sir. Like sir, in the recruitment process of DRD also, sir, there are very less vacancies for core electrical engineers, sir. Like electrical and telecommunication engineers are they are preferring more. Any reason for that, sir?
Actually, this because that's true. Actually, probably that may be true, but that depends because DRDO is a very big. I think I'm not very much onto the because DRDO is having 51 laboratories, which we are using almost different technologies. So that will come directly from our director Delhi. So that requirements that depends upon the thing because as far as missile complex is concerned, we are having good amount of electrical engineers requirement. But whatever you are seeing as a advertisement or as a recruitment, that comes from the total at a Delhi level. I mean, all India level. So that we don't know because means I am not actually in authority to answer those questions because I also not known. But as far as missile complex, because I'm working for missile, definitely electrical engineers is a requirement design. We have enough people and people are recruiting also. So that way, so you may be seeing probably at the whole DRDO, In that case, it will be less. Yes, because there are radar requirements, a lot of other requirements there where probably telecommunication electrical may be more.
Fine, sir. Thank you, sir.
Yeah.
Yeah. Any other technical
Sir,
questions?
Yeah.
sir, how can we make use of AI in defense?
Yeah, it's a very good question. It's a very good question. Actually, a lot of area which I've forgotten to tell you is one is the robotics. Actually, this in fact, already we have a AI lab in DRDO, which is working in, I think in Bangalore is there. And also we have in our RCA also an AI center where they're using AI for robotics, where we are using a lot of, in fact, I may not able to answer, I may not able to tell those things, but we are using robotics for different applications where the AI requirement is there, and we have set up AI lab in RCA also. And coming to the AI application to the electrical machines also we are doing, because as I told you, the fault diagnostics and fault tolerant electrical machines and drives, where we want to use an actuation system which is a complete fault tolerance, there definitely AI requirement is there. That is also one of the area. In fact, we are not worked on that. We have to work on that. But coming to the other lab, what I told already, RCA is that we are doing a lot of AI techniques for robotic applications.
Yeah. Good afternoon, sir.
Yeah, good.
I have one question.
Yeah.
Sir, can you please highlight what is the different operating voltage and current for the converters or the pneumatic systems which are designed for the guided missiles such as Prithvi or Agni, which you have highlighted
Yeah,
earlier?
pneumatic or electrical?
Yes, electrical systems
Yeah.
or converters,
Yeah.
sir. Size
Yes.
converters. Yes, sir.
Yeah. Understood. Power converter. So we normally, I will tell you, coming to the in a missile system, coming to the converters. One is coming to the BLDC motor. We have a power inverter which will come from the DC to AC, where normally the applied voltage will be in the battery. So battery voltages vary from 28 volts to 140 volts. So we have missiles where we're using 28 volts, and we have missiles where we're using 140 volts. So we have 28 volts, we have 56 volts, we have 70 volts, and we have 140 volts. So these are four levels of voltages we are operating with. In fact, 56 you can neglect, 28, 70, and 140. This is for the DC to AC conversion for BLDC motor application. Coming to the converter part, that is a DC to DC converters for all avionics, means all the missile consists of different subsystems. It will have an onboard computer, it will have an INS system, it will have some sensors, all those things. Everything should be powered from a DC because we have to have a battery. So battery is unregulated, so it will be connected to a regulated DC-DC converter. So the DC-DC converter normally operates from 18 to 36 volts input voltage, and output voltage will be 28 volts constant. So we have an input range 18 to 36 and output will be 28 volts. So that 28 volts will be given to the each subsystems. Like my actuator controller is there, it will take 28 volts from this DC-DC converter. So all missiles, we use DC-DC converters which are varying from 18 to 36 and 9 to 36 volts. So coming to this, one more just I want to give for information. All these DC-DC converters, most of the DC-DC converters we are not getting in India because all the manufacturers are very from outside the whole like Western countries. But major DC-DC converters, you people are presenting in a lot of conferences. All our Indian students and Indian professors, we are presenting a lot of papers in conferences. So this is also one of the area we want to have compact DC-DC converters with complete DMA filter inbuilt. So this is also one of the developments we want to make so that we can utilize our own product instead of depending upon the outside world. So that is so converters are being used left and right in all the missiles. So as per your question, everywhere we are using, and these are the ranges.
Yeah. Thank you, sir. Sir, just one question.
Yeah.
So, sir, the current ranges, does it go beyond 500 amperes or is it lesser than 500 amperes? Because actuators might be using a lot of current to.
Yes. No, but but the current requirement normally till now, whatever we have done, it has never gone beyond 500 amps. But because we are operating a little bit higher voltages, wherever we are going for the higher power, we are going for higher voltages. So maximum current till now we are handled is 300 amperes. So only on some applications we have gone up to 400 amps, where we are gone for IGBTs because the voltage levels are so more. So probably tomorrow we may have to go, but right now we are operating maximum at 300 amperes.
Okay. Thank you, sir.
Okay.
Hello. So is there any further questions or shall we end the session?
Sir, recently I heard that DRDO is going to set up laboratory at IITH. What is it about?
Yeah. Something is. I'm sorry about that. I heard that also, but exactly I don't know. Probably I may not able to answer that. But one thing I can tell, IIT and IIT Hyderabad and our RCI is setting up excellence at DRDO based on our beloved chairman, Dr. Satish Reddy. So I think one thing I could tell you that we have an interaction with IIT for PhDs. So that I think we are starting because I'm also involved in that, and we are just working out what are the topics to be worked out for, at least from electrical part, we are just working out. But coming to the laboratory at Hyderabad also, it's true. But exactly what type of technology, all those things, I don't aware at, frankly.
Sir, does DRDO recruit from campus?
Because this is
Excuse me, I'm sorry. I mean, please ask technical questions.
yeah. Because there is more towards the HR, I could not answer those things.
Hello,
Yeah,
sir.
yeah. So,
Sir. Hello, sir.
Yeah, tell me.
Sir, you are telling about control system design.
Yes.
Sir, still we are using PI controller, and what in the literature we are reading till now, till
Yeah.
MTech.
Yeah.
We are following that literature, or some advanced techniques are you
No,
are using?
actually, I'll tell you. In the control systems, it depends upon the application basically. Normally, we use PA control. There's no doubt. Whatever we are studying, same thing we are using in most of the applications because that is sufficient for most of the applications. But in some of the applications, we are going for adaptive control, or we are going for like I told you, disturbance control. Like for example, we require applications where there should be a difference between the no load and load. We should differentiate between, because in some of the applications the load requirements are all so stringent that you should able to have an algorithm to differentiate between the no load and load. Based on that, you should write your algorithm. For that purpose, we use something like a torque disturbance estimator. So some estimation techniques are available that we are using, but in general we're going for PA. But if you go for the complete autopilot design, which I'm not talking and I'm not an expert on that requires a lot of advanced control techniques. That already a separate group is there which will design the complete control system of the missile, because we are designing the control system of an actuation system, whereas they design the complete control system of the missile, which are also part of our RCA. Separate group is there where they use, definitely they're using a advanced control techniques, which where they use the non-linear control techniques to estimate based on your actually characteristics of the vehicle, based on the wind characteristics, based on the wind data. They will choose. That's what I'm telling, adaptive control. That type of techniques will be used. Otherwise, from actuation system, most of the thing it will be simple PI.
Okay, sir.
Okay. Any further questions are there?
Yeah, if there are no further questions, I think we will end the session here. And let me thank Dr. Ravikumar for his patience and staying back to answer all the questions. So thank you, Ravikumar. Definitely, we will be in touch with you if there are any further discussions continuing on this.
Thank you. Thank you.
So thank you.
Great. Thank you all.